Okay, lecture 7, cycloalkanes. There's some terms you should know. Now, when naming the cycloalkanes, we have to first determine what kind of cycloalkane parent we have, the parent ring. In this case, we have three carbons in a row. For a straight chain alkane would be propane, so this must be cyclopropane. You need that cyclo in there. Students forget that all the time. They'll call this ethyl propane. It has to be ethyl cyclopropane. Now, that is an ethyl group here. And so we'd make this ethyl, writing it backwards just so I don't leave a space there, ethyl cyclopropane. Now, students often want to put a 1 in front, but the thing is that when there's only one substituent, no numbering is necessary, and you don't want it in there. It's wrong. Because if we just see an ethyl group on a ring, that ethyl group has to be at position 1, so there's no need to put it in there. That's true whatever the ring is. This is cyclopentane. If we have a bromine, then this would be bromocyclopentane, not 1-bromocyclopentane. So whatever there's only one substituent, name it, attach it to the ring name, and no number. Cyclohexane, that's just, I guess, in there to make sure that you know the rings, the shapes of them. So we have cyclopropane, cyclobutane, cyclopentane, cyclohexane, and it goes on from there. It gets a little tougher to draw. Usually, for the students, I don't often ask, well, actually, cyclooctane isn't too bad. That's like a stop sign. The 7-membered one is a little trickier. I don't often have students do that, unless I'm just being mean. But as long as you get 7 sides on it, if I give you a cycloheptane in the exam, then that will do. Now, when there's more than one substituent, now we have to number them. And the reason why, these two methyl groups, they could be on the same one, same vertex, same carbon, or they could be across from each other. So there's the 3 possibilities. Well, since they're different compounds, but it's still, they're all dimethyl cyclobutanes. The numbering will tell us the difference between them. So we want the lowest numbers possible. So if we started numbering from here, this would be 1, 2. If we started numbering from this side, it'd be 1, 2. We certainly wouldn't start numbering from a carbon that doesn't have a substituent. So a 1 will always be found at a carbon that has a substituent. So you can forget about all the rest of the numberings, because here we could start 1 at any point and go in either direction. So there's actually 8 possibilities, but you can immediately get rid of 4 of them, because we wouldn't start at either of these. So the more you do of these kinds of namings of the cycloalkanes, you'll see that a lot of them, even though it seems like there's tons of ways of numbering, you can get rid of many of them just by realizing that some of these positions would be silly to start with, because you know that you're going to have too high of a number. So either side, either methyl group will give us the same numbering. So we call it 1, 2 dimethyl cyclo. Make sure you get that cyclo in there, butane, and get this right. Students will very often do 1, 2 dimethyl cyclo propane or something without thinking, without realizing that they know that it's cyclobutane, but they just make that mistake because they're rushing. Now for this one, we call it 1, 1 dimethyl cyclobutane. And then this one would be 1, 3 dimethyl cyclobutane. I won't go any further with that. But so you can see that when you have 2 methyl groups on this cyclobutane ring, there's 3 different ways they can be positioned. So that's why the numbering is necessary here. Now, if they're not the same substituent, this is methyl and ethyl, then we go by the second rule that's in your book. When 2 ring substituents are present, the numbering begins with a substituent of higher alphabetical priority. So if you have 2 of the same substituents, then you just number them with the lowest numbers. But when there's 2 different ones, you could start here, and there'd be 1 methyl and 2 ethyl. But you want to put the one with the substituent that starts with the letter that becomes before the other. So this is E, this is M, so this is going to be 1 ethyl, 2 methyl. Since there's no end here, it's a ring, we can't use the same kind of number. This goes along with the same kind of logic. But in this case, since we could start the one at either substituent, we go with the one with the higher alphabetic priority. Yeah, okay, so and this would be cyclobutane. So after that, then it's just whatever you were given. Let's say this was ethyl, and then you had this is propyl. Well, you'd start here, and you could go this way, 1, 2, 3, 4, 5, but 1, 2, 3 will give us the lowest number. So this one would be 1-ethyl 3-propyl cyclohexane. So when with two that are different from each other, that's actually even simpler than when they're the same type of substituent, because you can just find the one that's higher up in the alphabetical priority and start right there, and then just go around. Now, if we have, let's look at this one, 1,2,2,3 tetramethyl cyclopentane. Now, I wouldn't give you on the exam, so we'll call it 1, 2, 2, 3. I wouldn't give you this one to name. Well, this one is not too bad. But I'm not going to give you 4 or 5 or 6 substituents unless it is something simple like this. And that's definitely not something that would be too tricky to name. But I wouldn't give you a cyclooctane with 7 different substituents. But I will give you something like this, where you have 3 substituents. Now, this is a third rule. When there are 3 or more ring substituents, ring numbering begins at the substituent that leads to the lowest set of location numbers. So I'm going to I want to expand this out just because I want to do different numberings. I want to be able to draw them all, so I'm just making this larger. And I'm going to get rid of this here. Okay. Now, you can see that we have to start at this one or at this one. If we started here, then we'd have to, for 1, then we'd have to go 2, 3, 4, 5. So the 1, 2, and 3 have to be on these 3 here. Well, we can't start with the 1 at the ethyl group and then say 2, 3. We can't. We have to go in order. So if we start here, it's 1, 2, 3. If we go the other way, 1, 2, 3. And if you don't believe me or you don't see it, you can start with 1 here. Try it and see. And when you get done, you're going to have a higher set of numbers than I came up with. So since this is symmetrical, we actually come up with the same name if we from either side. So we have this is 2-ethyl, and then it'll be 1,3-dimethyl cyclopentane. And I'll use this thick pen whenever I can, where it doesn't get too bunched up. Now, what about this guy? Notice it's the same substituents, we just put them in a different order. Well, I might be able to work off of this. Well, we can see again that it's either going to be 1, 2, 3 or 1, 2, 3. So we have 1, 2, 3 or 1, 2, 3. Well, since we have the choice of having ethyl with a 1 in front of it or ethyl with a 3, and we're going to have the same numbering, 1, 2, 3, 1, 2, 3, we're going to go alphabetically. Here we have the choice between starting with a methyl or starting with the ethyl, and when we have that choice, and it's the same numbers, it's 1, 2, 3 for all of them, so the sets are the same. We go alphabetically. So 1-ethyl, 2, 3-dimethyl, cyclopentane. Should be on there. Good. All right. Now let's look at. I'm going to do the name to the structure here, and then we'll do a tricky guy here. So we have cyclohexane. Draw it out. Pick this as number 1. You don't have to, but why not? Just get into the habit of that. You can pick any of these, since we're going to be filling it in, we can make any of these 1 and go from there, but choose that as 1. There'll be 1-diethyl, so 1 and 2, and then we have 1-methyl, so 1, 2, 3, 4, 5, methyl here. And yeah, and that's the deal. Now for this guy, And let me just see, make sure, because you can write this down. So 1, 2, well, yeah, it does make sense that we have to go in this direction, 1 and 2, because this is definitely going to be 1 because it has the both substituents on there. What I'm just looking at is I wrote this out, but it doesn't, just because I have these numbers here and we can make it doesn't mean that it's right. That's the way that you should name it. But you can see this has to be 1 because it has 2 substituents on it, and we would go with the next substituent in order. This is 2, so 3, 4, 5. So this would have to be it. Just as an aside. And there's problems in your book where they give you a name and they ask you if it is right. So when you write out the structure, then you check and you'd rename it yourself and see if you come up with the same name. So yeah, everything's fine. I do these up, and sometimes I never check before I start, just to make it a little tricky and give me the same kind of feel that the students are going to get. Now let me expand this guy out. This is a cycloheptane, and I want to be able to write all the numbers out. Boom, 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 and I'm going to just put it there so that I keep it out of the way, or give me enough room to name it. Now, when we start this, we have six possibilities. We could start here with 1. Now we could name it 2, 3, 4, 5. We could go this way, but you can see that number is going to be way too big because we're not going to meet up with a substituent until the 5th carbon. So if we start with 1 here, then it'd be 1, 2, 3, 4. We really have to go in this direction. Now you can certainly number it in this direction too, but you can see already that this is 1 and 3 and 4. So if you went in this direction, you have 1, 2, 3, 4, 5. You're going to have a 5 there. So that wouldn't be 1. That'd be a higher set of numbers. So that's one. The one that we have here is a possibility. The other way would not be a possibility. Let's start with this guy. If we had this as 1, well, we'd have to go to the next closest substituent. So this would be 2, 3, 4, 5, 6. Okay, so that one's out because we have a 6 there. 1, 2, we have a 1, 3, 4. So far, it looks like the winner is 1, 3, 4, but we have one more possibility. If we start here, 1, 2, 3, 4. So if we start with the propane, or the propyl group, we get 1, 2, 4. We had 1, 3, 4 here, so the 1, 2, 4 wins. We'll get rid of the rest of these guys. So you can, I'm never going to give you more than 3 substituents, so really there's only 6 possibilities. And for each of them, you're going to probably find that one of them doesn't count, so you're really only going to have 3 possibilities. So write out all the numbers, and we end up with 2, and all the sets of numbers that you think are possible, and then just narrow it down to the one that has the lowest set of values. And this is heptane, or cycloheptanes. 2-ethyl, 4-methyl, 1-propyl cycloheptane. Okay, now that ring locks the substituents either above the ring or below the ring. And that's when we get this cis-trans kind of thing that can happen. And let me, I think I got a piece of paper here. Let me just, so if we take cyclopentane, and a lot of times it's drawn like this to kind of make it look like we're looking at a tabletop. You know, here it's like we're looking down on a this pentagon from the top, like a table that's a pentagon. We're looking straight down. But if we were to get a little bit above the table and look down at it at an angle, it would look kind of like that. We'd see that it seems to be tilted, and that helps us see. So if we have a methyl group above, both above, then we call this cis. And if we have, and then the other possibility is where we have one above and one below. So this would be like you had these 2 candle holders on top of the table. Here you have a candle holder above and then the leg of the table below. So the candles are right next to each other. This candle is above and the leg is below. And you can see the only way to get this substituent down is to break a bond. It's locked into place. with this ring. So these rings allow us this, and this is called trans, meaning across. Now, if these weren't different, didn't have different chemical properties, then we wouldn't care about it, but they definitely do. Just that structural difference where the substituents are locked above or they're across from each other, across that ring. One's above the table, one's below the table, that gives it different chemical properties. So what the question is asking, determine whether cis-trans isomerism is possible for each of the following cycloalkanes. Now the 1,3-dimethylcyclopentane, so I'm going to draw this out. So again, that tilted, like we're looking at a table from, like we crouched down in the chair at the table and are looking at it at a high angle. This is one methyl group. And what did I, yeah, I must have just caught the name here and subconsciously used it. But the cyclopentanes are really good ones for this. So we can see that we can either have this, or we can have this is cis, and then this is trans. We have them across. Now, the big thing here is there's no way of tilting or twisting or rotating this molecule to make it look like this one. The only way to get this group down to look like this is to break the bonds, to break the ring. Okay, now let's do 1,4-dimethylcyclopentane. Actually, this should be cyclohexane if it's going to be an actual thing, and I'm sure it was. Let's see, I meant it to be. So cyclohexane, and you can see the numbering shouldn't be 1,4-cyclopentane. Dimethylcyclopentane, it would be 1,2, so it doesn't really matter. They're next to each other, but let's use cyclohexane so it makes sense as far as the name. And there's a methyl group here, methyl group above, so same kind of thing as the cyclopentane. This is cis, and then this is trans. Now what about this 1,1? Now this one looks like, and this is cyclopentane, so we're going to just, again, 5. Now we have 1,1, so the methyl groups would be above and below. And you say, well, then, so you could say this is trans. Well, and then or think of this as trans. And then you say the cis would be like this. This isn't allowed. The ring can only have one substituent above, one below. So this is the only possibility. Since there's only one possibility, there's no cis and trans. It's not even trans. You don't even call it trans. You can't say, well, then it's only trans. No. Even though they're above and below each other, they're on the same carbon. The substituents have to be on different carbons on the ring to be cis or trans. And then ethyl cyclopentane. This one's pretty obvious because, yeah, this ethyl group, well, there's nothing countering it. There's nothing to be cis to. So even though this looks like trans, the methyl groups or the substituents have to be on different carbons because there is no counter to it. Even though you might think of this as trans, there's no cis, so you can't have the methyl groups on the same side, so on the same carbon. And that is that.